Okay, so let's do section 6.3. This section is the angle of parallelism. Okay, so this section is about constructing lines parallel to a given line. So in Euclidean geometry, of course, we have the double perpendicular construction, where we, given a line L and a point P, we can construct a line by dropping a perpendicular and then making another line perpendicular to that. And that gives us two parallel lines, M and L. Of course, we know in hyperbolic geometry that there is more than one line parallel to L, so there are other lines that are not necessarily orthogonal to this line right here. So I want to have a way of finding all of those lines. There's going to be actually infinitely many, so a bunch of these. So we want to be able to find all of them and know exactly which ones they are, and at what point does this actually go through. So if you pick an angle, is the line going to hit L, or is it going to do this? That's the goal for this section. Okay, so we're going to start with a construction. So we'll let L be a line and P an external point, just as we did with the double perpendicular construction. So I'm going to draw this as I do it. So here's line L and point P, and we'll drop a perpendicular from P to L with foot A. So that's here. Here's the foot. And then we'll let B, different point than A, be a point on L. So we'll put B over here. The point of this point B is just to choose a side of this line PA. So we're going to be doing things to the right of that. Okay, so now for each real number R, between 0 and 90 degrees, there is a point D sub R on the same side of PA as B. Such that the measure of the angle APD is equal to R degrees. Okay, so we pick an angle R, and then, so here's our angle R degrees, and then we just pick some point here, D sub R, and then we continue this line. Okay, so this is the construction. We're just constructing a line that goes through P that has an angle of R degrees with PA. That line may or may not intersect with L. Okay, so we'll come back to this, or really this definition will kind of tie in with it. So this is definition 6.3.1. And this defines the set, which we'll call K, which is R, such that the ray PDR intersect the line AB, which is, well, we want the ray AB, but this is part of the line L, is not empty. So these are all of the angles for which this construction gives an intersection here. Okay, so of course 0 is going to be in here, and there's going to be, of course, a lot of angles at R, but at some point there's going to be lines that actually don't hit L. And that's the point of just defining this set. So as I said, note that 0 is in K. And we also know that 90 is not in K. So K has to be a subset of 0, 90, where I don't include the endpoint 90. We know that 90 is not in K because we know that if I make this construction, these two lines are parallel. So this line definitely does not hit L. And of course we know also that there has to be some other one that does, because parallels are not unique. There has to be some other line that's parallel to L, and that's going to have some angle that's not 90. So there's got to be something. This has to be a proper subset of this. There has to be something else that's not in there. Okay, so now let me state the theorem. This is 6.3.2. So let K be the intersecting set for P and AB. So again, the intersecting set. Oh, did I not? Oh, shoot. Sorry. Let me go back to here. I did not finish this definition. I got distracted by my note here. So the set K, the rest of this is called the intersecting set for P and AB. So if I end up making a lot of mistakes like this, I'll probably edit the video to fix them. But if this is the only one, I'll probably just leave that in and force you to suffer through it. Okay, so this is called the intersecting set. And it's called the intersecting set because it's all of the angles for which the line intersects L. So aptly named. Okay, so back to our theorem that we're stating. So theorem 6.32 says let K be the intersecting set for P and AB. And if R is in K, then first S is in K for every S with 0 less than S less than R. And there exists T in K such that T is greater than R. Okay, so what is this theorem saying? So going back up here, this is saying two things. First of all, so if I have some R like this one that is in the intersecting set, i.e. there is an intersection here, then first it's saying if you take any smaller angle, so any S somewhere in between, so say S is here, well, let me just use a different color for this. So you take any S, say here, then of course that's also going to intersect. It has to, as we can see. I mean, we'll prove this theorem in a second also, but I'm just going to kind of give you the rough idea for why this has to be true, so you can understand what the theorem is saying. And then the second part says that there's always a bigger angle that's also in it. And that's just going to be true because I can just pick a point out here and draw the line from there to there, and this angle is bigger than R. Okay? Okay, so before I prove this theorem, I want to I want to make a definition which kind of shows us the consequence of the theorem. So theorem 6.3.2 implies that K is a half-open interval of the form 0, R naught for some number R naught, and that number has a special name because it's an important number. This is called the critical number for P and AB. Okay, so why does this theorem imply this fact? Well, so what's really used here to say this is the least upper bound property of real numbers. So we're using some heavy machinery from real numbers, which you will learn if you haven't already taken real analysis or advanced calculus. Then you'll see it when you take that. So I'm not going to go into the details of that. But you have some intuition about this just because you're used to dealing with real numbers. And the intuition is, well, I mean, we can just see from this picture that so the interval is either, 0 to some number with it closed, or it's 0 to some number with it open, right? There's only two types of intervals it could be. And it can't be this because, so if this were R naught, then I can easily just find something bigger than it that should be in that set, right? So there's no biggest element, right? And that's what's happening here, right? R naught is not in this set. So what the angle R naught is going to be is there's going to be some line that's the first one that is parallel, right? So this will be the angle R naught degrees. And if you look at the line at that angle, then every line at a smaller angle will intersect L. Okay, that's the idea. Oops. So before I move on to proving the theorem, let me just write down a couple of these consequences. So first of all, any ray from P that makes an angle of measure less than R naught degrees with PA intersects L, as I just said a minute ago. So this is strictly less than. And then any ray from P that makes an angle of measure R naught or greater with PA is parallel to L. So this R naught tells us the cut point between lines that intersect L and lines that are parallel to L, with R naught, the angle R naught denoting a line that is parallel, and everything below R naught being lines that intersect. Okay, so now let's prove the theorem. And the proof is just exactly the explanation I gave, but we want to make it a little bit more precise. Okay, so just the setup here, we'll let K be the intersecting set. For P and AB, and fix a number R in K. So remember, the goal, going back to the statement of the theorem, is for an arbitrary R, so pick some R in K, we want to show that anything less than R and bigger than 0 is always in the intersecting set, and there's always something bigger than R that's in the set. So this is basically saying it's a half-open interval. Okay, so we'll let R be the point at which PDR intersects AB. Okay, so let me start drawing the picture here. It's basically going to be the same picture as before, but with a little bit extra. So here's P. We drop the perpendicular to A. We have B here somewhere. We have some angle R, which the angle R is in the intersecting set, which means that this is going to intersect P. So remember, we construct that by finding some point dr here that gives us the angle. But dr isn't necessarily on P. So we're just going to look now at the point that, now that we know that R is in the intersecting set, we know that this point exists. So we let this point of intersection be R. Okay, so now if S is between 0 and R, then PDS, so here's S is some angle, and we get DS, which is the point we use to construct that angle. And now we look at the ray PDS. So PDS is between PA and PDR, right? And that's just comes from the fact that the angle S goes from PA in this direction, and it's less than the angle R, so it has to be between these two rays. So then PDS must intersect AR at a point S. This is by the crossbar theorem. So there's some point S here where it intersects. And so this means, by definition, that S is in K. Right, because K is the intersecting set, we see that the ray determined by S, the angle S, intersects L, so it's in the intersecting set. Okay, so that's the first statement. And then the second statement, first we consider the case where R is equal to 0, because in the second statement, here it's not assumed that, or I guess it's T, we're going to call it T. Not assumed that T is not equal to 0, so we need to consider that case. Sorry. So here, it's not assumed. Here, it's not a, dang it. Here, there we go, there's the pointer. Here, it's not assumed that R is not equal to 0. Right? R is just something in K, 0 is in k, so we need to consider the possibility that this is equal to 0, that r is equal to 0. Of course, that's going to be easy to deal with. If r is equal to 0, then t equal to the measure of APB is greater than r, right? So basically, if r is 0, and I want to find an angle bigger than r, bigger than 0, well, I already have this b here that I can just use, and this is going to give me some positive angle, and that'll be my t, so that gives me some t that is larger than r that is in the intersecting set. Okay. So if I make that my t, then t is in k. Okay, so otherwise, if r is not equal to 0, choose a point t such that r is between a and t, and define lowercase t to be the measure of angle APT. So here I'm just going to pick some t here that's to the right of r, right? So I have a, r, and t. So r is between a and t. Right, so basically I'm just picking some t further to the right, because then if I look at this angle that I get from connecting p to t, then that angle, lowercase t, is going to be bigger than r. Okay, so the conclusion, since PDT intersect AB is not empty, because that intersection is the point uppercase T, we have that T is in K. And moreover, of course, T is greater than R by the protractor postulate. Okay, so that proves that theorem. But again, really, the proof is very simple. The proof is just, well, clearly I can find an angle less than this. I can just pick anything in between, and I can pick something over here to get an angle greater than. That's really all there is to it. Okay, so now another definition. So this is definition 6.3.4. So now suppose that P, A, and B are, as in the definition of the intersecting set, and that R sub 0 is the critical number for P and AB. So basically I'm saying picture is the same as it has been. So the picture I have my P, my A, B over here, and R naught is the critical angle. So if I draw something at the angle R naught, then it will be parallel to L, or to AB, if you like. And anything less than that, if I draw anything that's even a little bit less, it's going to intersect it somewhere. Okay, so then we'll let D be a point on the same side of PA as B, such that the measure of APD is equal to R naught. So D is a point on here. So basically I want to be able to identify this ray that is angle R naught from P. And so the angle APD is called the angle of parallelism. So remember, angles are not measures of angles. So R naught is the measure of the angle of parallelism, but the actual angle is the union of the two rays. So APD is the angle of parallelism. In other words, this is this ray union this ray. If I were to look at the measure of APD, then of course that is R naught, and that's just by the definition of the angle. Right, so the critical number is the measure of the angle of parallelism. The angle of parallelism is the, it's sort of the smallest angle where I get a parallel line. Of course, if I made any larger angle, I would also get a parallel line. I have all of these, everything in here is going to be parallel to L. Okay, so notice that this whole time we've just been working on the right side, right? This line, of course, goes in both directions. It goes in this direction also. So we could have done all of this in this direction as well. So we're going to have another angle in this direction. So I could have chosen B to be on this side. I'll call it B prime here to distinguish it from B. But I could have just as easy chosen B to be on this side, and that would have given me some D prime here, and it would have given me some angle here. So really, there are two angles of parallelism. So since B can be on either side of the two sides of PA, there are two angles of parallelism for a line L and external point P. So natural thing to wonder then is, well, what's the measure of this other angle of parallelism? And it turns out that it's going to be the same. This is also going to be R naught. And in fact, the theorem that we're going to prove next is that this angle only depends on this distance. So, in other words, if you take any line in the hyperbolic plane, and you take any point P, if the distance here, so let's call this line M, maybe I'll call this point Q. If the distance here from Q to, say, call it A prime, is the same as the distance here from P to L, then this angle of parallelism will also be R naught. So the angle, or I guess that's the critical number, but the measure of the angle of parallelism will also be R naught. And so the angle only depends on the distance. It doesn't depend on the line or the point, or you can move this around. It doesn't matter. It just matters how far you are. Okay? And so that we will prove that next. I'll state it as a theorem in a sec. I'm just first going to state it informally. So the critical number R naught only depends on the distance from P to L. Only depends on the distance from your point to your line. Okay, so let me state that more carefully as a theorem, and then we'll prove it. So this is theorem 6.3.5. I guess the statement is not any more careful. It's a pretty simple thing to state. It's just that the critical number depends only on the distance from P to L. Okay, so it doesn't depend on what the line is, it doesn't depend on what the point is, just the distance. Okay, so let's prove this. So let L be a line, so pick some arbitrary line, pick some external point, and let A be the foot of the perpendicular from P to L, B be a point in L not equal to A, so we're just kind of getting the same setup as we had before. So we have our line L, our point P, our foot A, B, and now we're going to let P prime, L prime, A prime, and B prime be another configuration of lines and points such that the distance from P to A is equal to the distance from P prime to A prime. Okay, so I have some other, L prime, some other P prime here, A prime, B prime. Now we'll let the intersecting sets be K and K prime. And let's take some R in K. So our goal here is to prove that K is equal to K prime. Goal K equals K prime. So these are two subsets of the real line, the real numbers. If we want to prove that two subsets are equal, we need to prove that K is a subset of K prime and K prime is a subset of K. So the strategy is we take something from K and we show that it has to be in K prime. Then we take something from K prime and we show that it has to be in K. And that'll show that the two sets are equal. So that's why we're starting with something in K, we're now going to show that it's also in K prime. Okay, so we have our R, then PDR and AB intersect at a point T. So we have our angle R, and it's constructed with a point dr. And since R is in the intersecting set, this has to intersect this at some point T. Okay. Now we're going to choose a point T prime on A prime, B prime, so that A prime, T prime equals A T. Okay, so we already have that PA is equal to P prime A prime. And so now I want to look at AT, and I can just find a point T prime over here so that this distance AT is the same as the distance AT prime, or A prime T prime. Okay, of course, this is a right angle, and this is a right angle. And of course, I can connect P prime to T prime. And now I have two triangles, and they have a side, an angle, and a side that are equal. So these triangles are congruent. So then the triangle PAT is congruent to the triangle P prime, A prime, T prime by side angle side. So that means that R is in K prime, right? Because that means this angle has to be R because these are congruent triangles. If this angle is R, then, well, the line, the ray with angle R intersects L, so that means R is in the intersecting L, K prime. Okay, so I have R and K prime, and of course, so now I know that K is contained in K prime. Of course, to show that K prime is in K, we just do the same thing but backwards. So it's the same proof. Start with R and K prime, construct the angle, and then find T so that A prime T prime is equal to AT. It's just the exact same thing, but with the primes switched. So I'm going to skip the details and just say similarly, R in K prime implies that R is in K. So therefore K is equal to K prime. Okay, so they have the same intersecting set, two pairs of lines and points. If the distance of the points to the line are the same, then the intersecting sets are the same, which means that the critical number is the same. Okay, so now we have some better understanding of how this collection of parallel lines is organized in hyperbolic geometry. We want to take this a little bit further though. So definition 6.3.6. So the next thing we want to do, so let me scroll back to this picture. So we know that we have this special angle, which is sort of the first angle where we get a parallel line when we go out from P at that angle. And we know that all these lines are parallel. And we know that what this angle is only depends on this distance. So the next question is, well, how does it depend on this distance? If I make this distance longer, so if I put some Q out here, is the critical number at this point going to be bigger or smaller than R naught, than this critical number? And it turns out it's going to be smaller. The further you go away, the smaller the critical number is. You can kind of think of it as you have more time to turn to the left if you're further away, right? So if you're really close, like here, you don't have much time to turn to the left. This line is really close to you, so you're going to have a very large critical number. You have to be close to 90 degrees. But if you're really far away, like here, there's plenty of time to turn to the left. You can have a very small angle and still eventually have time to go this way, and it's parallel. So that's the idea. The distance, greater the distance you are from the line, the smaller the critical number. And that's what we want to show next. So toward that end, we need to make another definition. So given x greater than 0, let P and L be chosen so that the distance from P to L is equal to x. Define kappa, so this is not a lowercase k, it's the Greek lowercase kappa letter. So kappa of x to be the critical number associated with P and L. So by the theorem that we just proved, which was theorem 6.3.5, kappa is well defined, is a well defined function of x. In other words, x is the distance, right? This is saying that the critical number only depends on the distance. So we can have this function where for any given distance, I can tell you what's the critical number. That's what this function is doing. You give me a distance, I tell you what this critical number is. That's the measure of the angle of parallelism. Okay, so by theorem 6.3.5, kappa is a well-defined function of x, does not depend on our choice of L and P. The function which we're defining, kappa, which goes from 0 infinity, because it's a distance, so it has to be bigger than 0, to 0, 90, is called the critical function. So this is the function that encodes all of the critical numbers. Give it a distance, it spits out the critical number for that distance. And so this theorem is the theorem that tells us how this function behaves. So this function kappa from 0 infinity to 0, 90 is a non-increasing function. Oops. In other words, if A is less than B, then kappa of A is greater than or equal to kappa of b. So if your distance A is less than your distance B, then your angle, your critical number is greater than the critical number at B. So this is saying that given a line, the further you are away from the line, the smaller your critical number is. If you get closer, bigger critical number, bigger angle of parallelism. So this theorem is saying exactly what I was explaining before. Okay, so let's prove this theorem. So this is really what we need to show. This is, definition of non-increasing. Okay, so we're going to start with our assumption, choose A less than B, and try to prove that this holds. Okay, so let A be less than B. We need to choose points P, A, and B, and D, so that PA equals A, and APD is the angle of parallelism. For P and AB. Okay, so let me draw a picture. So I have P here, A, B, D. Let me do better than that. And this is R naught. Or I think for this we'll just call it R. So this is the angle of parallelism. Then we'll choose Q in AP. So Q is going to be in this ray, so it's somewhere up here. So that QA equals B. Okay, so this distance equals A. So this is A. And this distance equals B. And now let R equal measure of angle APD as shown, so R is there. And choose E on the same side of AP as B, so that the measure of AQE is equal to R. Okay, so somewhere over here I have an E, so that I also get an angle R here. So then the line QE is parallel to PD, so QE intersect AB is empty. So why is why is QE parallel to PD? If we were in class, I would probably ask you this and force someone to answer it. But it's simply the alternate interior angles. So I have two lines here and a transversal and alternate interior angles that are both equal to r. So the alternate interior angles theorem tells me that this line PD is parallel to this line QE, right? So I know these lines are parallel. In other words, if I continue this line further, it's not going to intersect this line. So certainly it can't intersect this line because it obviously would have to pass through this line to do that. So QE, this line, also does not intersect AB, this line. So that means that R is not in the intersecting set for Q and AB. So the critical number for QAB cannot be greater than R. In other words, kappa B is less than or equal to kappa A, which is what we were trying to show. Okay, next thing that we want to show is that, in fact, every critical angle is acute. It can't be 90 degrees. This I've already kind of hinted at. It kind of follows pretty easily from the fact that there are more than two parallel lines through a point. So they can't both be 90 degrees. But we want to be a little bit more careful about this. So every angle of parallelism is acute. In other words, another way to say this is every critical number is less than 90 degrees. Or you could also say it as the function kappa that we've been talking about, which before we had defined as going from 0 to 90 with a square bracket on the side. Now we can say that this is a round bracket because the critical numbers are never 90. Okay, so let L be a line, P an external point, and A the foot of a perpendicular from P to L. And then let M be a line through P with M perpendicular to PA. Okay, so we have L, we have P, drop a perpendicular to A, and then we construct a line perpendicular to that, call it M. So by the hyperbolic parallel postulate, there exists a line in that's not equal to m, so that n passes through P, so P is an end, and n is parallel to L. N is not perpendicular to PA, because if it were, it would just be M, and we know it's not M. So the angle of N with PA is less than 90 on one side. And this angle measure cannot be in the intersecting set. Right, so there's some line N that does not intersect L, has this angle less than 90, and that tells us that, well, the intersecting set has to be less than whatever this angle with N is, or rather the critical number has to be less than this, so it's less than 90. So therefore, the critical number is less than 90 degrees. And that wraps up the proof of the theorem, and that actually wraps up section 6.3. Okay.